We'll start our session, and I want to free myself from the notes of the book. I think I'll be able to do this way more to worry about less constraints. Okay, so I'll discuss the control system design. So this is what we want to do: control system design. Please, we started the class using root locus method. Okay, this is what we want to do. So we said that last time that the controller objective is objectives of the controller meet the steady state system specs. So we want to meet the steady state error performance. Okay, and here we're talking about ESS due to ramp, position constant, acceleration, and so on. Okay, the second thing, we want to fix the transient performance, or in a better word, say that we want to meet the customer specification for the transient performance. Here we're talking about overshoot, we're talking about rise time. Customer will not probably tell you rise time unless he's a good engineer. Maybe they will say, I want a fast system. Okay, and the settling time. So these are the things that the controller is designed for. Okay, so I want to start with an example. Okay, and we want to work first on the first requirement. So we want to fix or meet steady state performance. We want a system to meet a steady state performance. And here I want to start with a simple example. Okay, so I want to start with a simple example. So let us consider, and the controller that normally meet the steady state performance, we call them either PI controller or lag controller, and we will show you the difference. So from the outset, I'll tell you that we're talking about PI controller or a lag controller, and these are meant only to make a steady state performance, to fix a steady state performance. And you have to understand that the lag controller or the PI controller, to fix the steady state performance, to improve the steady state performance, on the other hand, they make the transient performance worse. They make the transient performance worse. So you have like a fixed resources. So if you gear your resources towards something, you pay less attention to the other resources. Okay, so this is how it works. So we want, therefore, their impact on the transient performance to be minimal. Okay, this is the idea. So I want to start with an example, a second order example. In the book they started with a third order example, which makes it more vague to understand. I will start with a second order example because you should know on the fly how to do a second order example. So suppose let us have the following system: a system where G of S equal 1 over S times S plus 1. Clear, right? This is what is the type of this system? It is type 1 system, system type equal 1. The customer comes to you and he wants the steady state error to a ramp be less than 5%. So he has a ramp of velocity input basically, and he wants the velocity error to be less than 5%. Okay, so you start your design by the following. You will say that, okay, my system, let me check if I can do the first, let me write a step here, maybe better. So first step, steps. Check if the system performance can be obtained or attained by simple proportional feedback. So the first thing, why should I worry about more designing a more sophisticated controller if a simple proportional feedback works? Okay, so I will start by saying, okay, I want then to put a simple proportional feedback, and this is KP, proportional feedback, and I want to put, this is my plant, which is 1 over S times S plus 1, and okay, so this is my input, let's say this is R desired, and this is C. So you want C to be equal to R desired. This is, of course, the error here. Yeah.
So if you want ramp, why are we using KP?
This is KP, the proportional feedback constant. It is not KP. Not every alley is okay. Not the same, right? We are talking about different things. KP. This is not the position error constant. Clear? Understood? This is not the position error constant. This is KP, or the feedback, the proportional feedback constant. It means that if I use here U, if I note this as U equal KP times the error. So this is why we said this is a proportional feedback. Yes?
We still need to check the stability of the...
Well, that's right. We need to check everything. Okay. So the first thing, we check the proportional feedback. And now we can check everything, the stability and the system performance dynamics using a root locus. So the second step to plot the root locus of the closed loop system. So we want to put plot the root locus, and this is a very simple system, and you should, without wasting time on steps, you should tell me what is the root locus here. So you have a pole at 0, you have a pole at -1. Okay, so this is a second pole. So the root locus simply, we have two roots here, and we have the asymptotes. We have two asymptotes, and this is minus this point is minus 0.5. So this is the root locus. Right? Correct? So this is the root locus of the system. When the system is stable, right, is stable. There is no problem with the stability. Now, let us check the steady state performance. The steady state performance, KV, because this, so let us, step number 3. So we did plot the root locus, check the steady state performance. And since here we are given a ramp input, then we need to calculate KV, which is the limit as S goes to 0, S times G of S and this is equal the limit as s goes to 0.
So G is the forward, right?
Yeah, s times k p times 1 over s times s plus 1, which is equal kp, right?
Okay.
This is kp, not the position error constant. Okay.
Okay.
Yeah, the gain. So this is the gain. Now, for the system to meet the performance, to meet the steady state performance, kV, the error is equal 1 over kV, which should be less than or equal 5 over 100, right? So kV should be greater than 20 or equal. And therefore, since kV equal kb, therefore kb should be greater or equal 20. Now we need to find where are the roots for that correspond to k p equal 20. So step number 4, we find the location of the roots. Find the location of the roots. What we mean by this, finding the location of the roots, this means that we need to check the transient performance, because the transient performance depends on the location of the root, right? Okay, so we need to let us check the closed loop poles of the system. So where are the closed loop poles of the system corresponding to Kp equal 20, right? And this is the characteristic equation determine this, which is 1 plus Kp times 1 over s times s plus 1 equals 0. This determines the location of the roots, which is s squared plus s plus kp equals 0, and kp equal 20. So this is s squared plus s plus 20 equals 0. What are the roots? Can you find them? So s equal minus 0.5, because zeta omega n is 1. So minus 0.5 plus minus, what is it?
Minus 0.5 plus 4.4 I.
4.4
4.
I.
And also, yeah, minus 0.5 minus 4.34 I.
Yeah, this is the conjugate, right? So this is what we have. Now what is the value of zeta here? What is the value of zeta? Zeta omega n equal what? Equal 1 over 2, right? 0.5. And therefore zeta equal 1 over 2 omega n, and this is 1 over 2 square root of 20. So what is this value zeta? Zeta, what is the value of zeta? It's like 0.0. 0.11. Okay, so 0.11. Now let me go back to my root locus. Where are my roots here? The closed loop root. So they are very way up here, right? Okay, so if I continue the root locus up here, probably they will reach the ceiling. This is the closed loop. So if I want to sketch the closed loop, what is this angle here? What is this angle here? This is zeta equal 0.11, right? This is zeta equal 0.11 line. Now what, can you tell me what is the problem with this location of the root?
The real part is small compared.
The damping is very small, 0.11. The damping is very small. The overshoot will be very high for this system. The overshoot will be very high. So if I need to meet the steady state performance, what is happening to the transient performance? It's getting very worse, right? Very bad. So here we can conclude, say that, okay, number 5, here, the location of the routes to meet steady state performance is or has very little damping. In this case, it is 0.11. The overshoot, the MP percent overshoot is too high. So if the customer tells you, no, I want my overshoot to be less or equal 5%. The customer tells you, okay, I don't want, well, I'm not interested in your solution. I want my overshoot to be 5%. So 5% overshoot correspond to zeta, 5% overshoot, yes, MPO correspond to zeta equal 0.707, which is the 45 degrees. If we go to the root locus here, the 45 degrees, I will sketch it here in green. This is the 45 degrees. This is zeta equal 0.707. The customer is happy with what? With the settling time. The settling time, what is the settling time in this case? What is the settling time?
4 over 0.5.
4 over 0.5. It's 8, right? 8 seconds, so it's maybe too long, but the customer is not worried about it. He's worried about the overshoot, right? He does not want this overshoot. So, therefore, we are happy with the root locus, except that the closed loop pole, when I am meeting the steady state performance, is making the transient performance very bad. So we want a controller that preserves the root locus. But the K here, if you look here, what is the value of K here? What is the value of K here? K equal 20. KP. What is the value of KP here? It is much less. We can find it out. Actually, KP here, we can find, let us find it out. So in order to meet the customer specification, we will have S squared plus S plus omega n, right, plus omega n squared equal 0. Okay, the customer wants zeta omega n to be, we have it 0.5, he is happy with this, but he wants zeta to be 0.707, and this is equal 0.5 over omega n. And therefore, omega n equal 0.5 over 0.707. What is omega n here? 0.707. 0.707. So omega n equal 0.707 radian per second. So this is the omega n that the customer, the MP overshoot needs to meet the MP overshoot of 5%. Okay, what is K in this case? Kp equal omega n squared, right? Which is 0.5, right? 0.5. So Kp equal 0.5. Now what is, you see the variation in Kp? Kp for the steady state error equal 20. Kp for MP overshoot equal 0.5.
So we can set two Ks.
Well, we cannot. We have to have a K which is satisfied the overshoot and move the roots down along this line. Slide them down so that basically I want K. If I go to my root locus here, what should I do? Let's say this is my root locus. Yes, I want to move K equal. That correspond to Kp equal 20. I wanted to move it here. Basically, I want to increase the gain on this leg. Instead from 0 to 0.5, K equals 0, K equal 0.5 here. I want K to be here equal to 20. I want K equal to 20. And how we do this? When I have the controller the simple controller is not good enough. So we need to design a controller. How much gain boost I need to do? 20 over 0.5.
40.
20 over 0.5, 40. So I want, the ratio is 40, right? So I want to push the gain by 40. Yeah. Well, we need to calculate the amount of gain increase. Just a minute, okay? Yes.
We're just gonna ask about Kp.
Yeah.
We found Wn is equal to 0.70.
Mhm.
Just put it.
Yeah, because this is I thought you understood this, right? Because this is, if you look at our system, 1 plus Kp over times 1 over S times S plus 1. So this is S square plus S plus Kp equals 0. So Kp is omega n squared, right? So Kp here, Kp equal omega n squared. Okay, so that's why I did not, let me just put it in a box. So this is a footnote basically. Okay, now this is the amount of gain increase. So I want now to look into a controller which is a different controller because the proportional controller is not working, right? Okay, go ahead. So I want to look into GC. This is 1 over S times S plus 1. And well, I used to have I used to have a system which I bring to the class and show you physically, okay? But with the MyRio now, we can do. I'll show it to you on MyRio, and you will carry your project on MyRio, so we can all see this in practice here in the class, huh? MyRio, you did not attend the session with Ali Wadi. You did?
Yeah.
MyRio is the device that he used. This is called MyRio. It's a national. Huh? He did not. Well, he did not tell you the name. Fine. The name of the device is called MyRio. MyRio. I will maybe put or instruct you or make an instruction about it. I thought he went through this for you.
He showed us how it works.
No, but did he explain to you the MyRio itself? No, no. Did he explain to you the LabVIEW, right? Yeah, okay. So I'll go through the MyRio is simply a national instrument product that you use in the measurement lab. You use national instrument. You use MyDAC or what?
Use that.
USB DAC, right?
Yeah.
There is something called MyDAC. It's a small white piece that National Instruments have. I don't know if you have it in the lab or not. It's a DAC system, data acquisition system. MyDAC, LabVIEW, they came up with a new product called MyRio. MyRio, they added to, MyDAC was meant only for acquiring signals.
Yeah.
MyRio, they added sensors to it. They installed on this bit accelerometer, gyroscope, rate gyros, temperature sensors, and they did instrument it. Okay, they did put measurement system on board, and they added to it also motor controller. So you can now control a system with MyRio. You can drive motors basically.
So you don't have to connect the sensor to that.
Yeah, you can have the unit. It has the accelerometer, the temperature sensor, the all basic measurements. Basically, you have them on board, and you have a motor controller. So if you want to implement this to control something, you can do it easily. And it's called MyRio. I think they are coming with a new product now. It's called probably will buy it. It's called My Robo or My something. It's more basically a kit that is used for robotics, for building robots. Okay. It should have more functionality than MyRio. It's another product basically. Now, yes. Yeah. Well, let us brainstorm about it. Okay. Now you can see that my controller is not doing well. Okay, my proportion controller is not doing well. But you already have a background that you can suggest a controller yourself. I don't need to tell you what you need to do. Probably, I'm sure some of you will suggest to me a controller if you understood the material well. Okay, what kind of controller we should add that will improve the steady-state response?
Proportion integration.
Well, this is a general because the proposed PID is used for all.
What's the question again?
How we improve the steady-state performance of the system? PD. No, it's not a PD. You remember that improving the steady-state error of the system, if I increase the time of the system by 1, right, I reduce the error. So the ramp error becomes 0 all of a sudden, right? So the ramp error for any combination would be 0. So I don't need to worry about the error in this case. So what is the solution for this? To add an integrator. To add an integrator. So if I come back here to my controller, so this is the first solution. I'll divert now. I'll discuss 2 solutions. First solution, we want to add integrator. We want to add integrator, look at the system and see how the system performs. So if I want to add an integrator, so okay, so solution, how we solve this? Okay, first, A solution, add integrator. So my controller becomes now, I have the KP, it is still there, and I want to add a KI over S and add them here. And this is my G of the system, which is 1 over S plus times S plus 1. And this is C and this is R. Is this clear? Is this clear? Now look, effectively what I did, this is R, and these are parallel paths. So I have this becomes KP plus KI over S times G, okay, and this becomes also, if I want to reduce it further, this becomes KP, okay, and here I have S, and here I have 1 plus KI over KP, right? This is S. This is S here, right?
KP, right?
KI over KP, right? So times G. Is this clear?
How did you make KP plus PI over S?
Well, how did I do this? How did I do this here?
Yeah, from that one to that.
Well, I took KP out and I made,
Okay.
yeah. So this is now my root locus. Let us look at the root locus now. And did we solve the steady state error? Here, did we solve the steady state error? We did. Of course, this is a type 2 system. KB now is infinity. Yeah, the error is 0. KB is infinity. Now I solved the error permanent. I have no problem with the steady state error. I need to check only whether I make this, alter the transient performance or not, whether I will achieve the transient performance or not. Now, what is the parameter that we need still to select? We need Ki over Kp. Ki over Kp. This is the parameter that we need to fix Ki over Kp. Okay, so how we select Ki over Kp? Now let us see. Now my system, my root locus becomes now. So I have how many poles at the origin? 2. I have 2 poles at the origin. I have my original pole which is at -1, right? And I want to maintain what? My asymptotes, I don't want to change them, because the idea is that the customer is happy with what? With the settling time, right? He is happy with the settling time. Therefore, I am happy with the asymptote at -0.5. In order to make the asymptotes basically stay at -0.5, where should the 0 be? No, it should be very close to the 0, because adding the 0, it will move the asymptote to the right. It will move the asymptote to the right, because the intersect of the asymptote is the pole minus the 0, right? Over the number of poles minus 0. Okay, so we need to have the 0 to be close to 0, close to the origin. So we need to have, in order for me to have my asymptote here at approximately -0.5, I need to put my 0, I'll make it in blue here, I need to put it somewhere here, very close to the origin, very close to the origin. Now if I check the asymptotes, sigma for asymptotes, this is the idea, sigma for the asymptotes, -1, -0, -0, minus Ki over Kp over 2. So in order to maintain the shape of the original root locus, I need to have what? Ki over Kp very small. Ki over Kp need to be very small. And so let Ki over Kp be, for example, 1 over 100, 1 over 20, etc. So that's the value that we select. Okay, so if I select Ki over Kp to be select Ki over Kp to be for example, 0, 5, right? So I will be, I am placing a 0 at minus 0.5, right? Minus 0.05, minus 0.05. I'm placing a 0 at minus 0.05, so it will not affect the root locus. If I zoom in here, what is the root locus now? How the root locus will look like? So this pole will go to the, from the following the principle, the construction method for the root locus. So I have a branch here, right? Now, because this is double pole at the origin, we cannot have between the 0 and the poles at the origin and the 0 a branch, because we have even number of poles and zeros to the right. Okay, so this pole, how the root locus will look like? Can anyone suggest? Can anyone suggest how the root locus would look like in this case? So we have so the root locus, of course, the asymptote should be part of the root locus when k is large.
Which one is the asymptote?
This one is the asymptote. It won't be at minus 0.5, it will be at minus 0.45 something, 48 for...
In this case, they don't have two points coming.
Well, no, in this case, I'll do it on the board here. Well, if you do it, I don't want to open MATLAB. You have, now, you did some research in MATLAB, so you should be able to use it. But because, you see, because the poles here, I will zoom in more. And so this is the 0 here, and the second pole is somewhere here now. If I, remember, this is minus 0.05, and this is minus 1. Okay, so this is very short distance. So this cannot be part of, so if I do the root locus here, what would be the root locus? Where is the root locus here? So the asymptote is minus sigma equal minus 1 plus 0.05 over 2, which is equal minus 0.95 over 2, which is equal almost minus 0.49, right? 475. Okay, 475. So the asymptote here I have at minus 0.75, so minus 4.75. So this is almost half. Okay, so this is the asymptote. Remember, the original asymptote is somewhere here. This is the original asymptote. So I did change this. I did shift it. Okay, but I cannot do without shifting it, because this is the dynamic system. Okay. So there is. I told you that if I fix something, the other thing becomes worse, right? Okay. So there is. So this is the system here. Now what happened? When there is no difference, there is no much difference in performance between this and this. Now, how the root locus will look like? Here, some of you would say, okay, and the root locus it will go like this, right? Okay. Well, I'll tell you, because this is very close. The distance is very far from this pole to the 0 compared with the location here. These two roots might go like this, and one here go root, and then one come and meet this root here, and then they split along this this asymptote.
So because both of them are initially attracted by the zero?
Yeah, because both the 0 is always an attraction point for the root locus. Because the two poles at the origin very close to the 0, if they might reach the 0, one of them reach the 0 before the far pole reaches the 0. Okay, so you have to check what we have to check. You have to check the breakaway point. Because here, how many breakaway points we will have? Three. The one at 0, 0, which is already there. Then the one that is this one here, okay, and then this one which is here. So we will have 3 breakaway points. Okay, so you can check your breakaway points. If there are 3, then definitely this is the case. If not, then if there is no just the breakaway point that you get 1. You cannot get either 1 or 3. Either 1 or 3. Right? Either 1 or 3. Yeah, because 1, this is the 1. This is the root locus can go in this direction. This is a possibility. And the second one, if they go here, then this segment of the real axis will have always 2 roots. Right? Will have always, so it has to split again. To branch, to go to the asymptote. How many people following me on this? Yeah? Okay, the breakaway point. If we have, if these roots, 2 roots, this is 2 roots. Okay, if these 2 roots to come and join here, okay, then one of the roots will go to the 0, and then the other root will go along this branch, along the real axis. And there is another root coming from the left here. They have to split. So we will have another point where we have double equal root, and then this will split like this. Okay, so the root locus here, this is K, P1, let me call it. This is K, P2. This K, P1, we have double roots. K0, we have K equals 0, Kp equals 0, we have 2 roots. Okay, this Kp1, we have 2 roots. This Kp2, we have 2 equal roots. 2 equal roots, 2 equal roots, 2 equal roots. Kp1, Kp2 greater than Kp1, greater than Kp0, which is greater than 0. Is this clear? Yeah.
I have one question. Sometimes the asymptote is horizontal.
No, the asymptote horizontal, we have the case with where the 180 degree, the horizontal asymptote, right? But along the real axis, the asymptote, we can have asymptote along the real axis, of course.
But above it,
Can you get? Huh?
horizontal above it, only on the axis.
With horizontal, you can give asymptotes in any direction, okay? Because if they are not on the real axis, they can be, of course, symmetric. Yeah. Then we can have, well, the asymptote, the number of, the difference between the force and the 0. 180 over the difference between force and 0. So if you have the difference between force and 0 is 10, you have 180 over 10, so you have the 18 and minus 18 and so on and so forth, right? You have 2 many asymptotes. Okay?
But the difference is 1, so it's 180 over 1.
When you have one pole, this is clear, right? This is 180. When you have one pole, the real axis, when you have one pole, so you have a system with one pole. This is a system with one pole here. So the whole real axis is the root locus here. The root locus is very simple here. So this is the asymptote and the root locus itself. Is this clear? So, you know now why we want to get the 0 very close to the 4. Okay, very close to the origin. Now let me show you why else we want to do this. Why else we want to do this? So we know that from our performance criteria that we want zeta to be 0.707, right? Okay, so this is the desired location of the roots. Now, from the magnitude condition and the phase angle condition, you remember that when in root locus we have 2 conditions, magnitude condition and phase angle condition. Everything boils about these 2 conditions. Now, if you look at the controller, 1 plus Kp times S plus Ki over Kp over S times G equals 0. The magnitude condition says that S plus Ki over Kp over S times G equal 1 over K, the magnitude. right? The magnitude of each term. What is the magnitude? Can you tell me what is the magnitude of S plus Ki over Kp? What is the on the graph? Where is it? Where is it? This is it. This is it, right? This is the magnitude. This is the one, right? What is the magnitude S? This is the one. Remember, S equals 0. This is the one. So these two values, are they equal?
Almost.
Almost equal, right? Almost equal. Almost equal. Okay. What is their angle? What about their angle? Almost the same, right? So we are satisfying the angle and magnitude condition. And remember, the difference between the pole angle and the zero angle is what? Which angle is bigger, the pole angle or the zero angle? I'm talking about the controller.
That's 0.
The pole angle is greater. The pole angle is an external angle to the triangle, right?
Yeah.
So this angle here, this angle here, this angle here, equal the zero angle which is here plus this angle here. So the difference, you see the small angle, the PID controller need to maintain a small difference angle. Otherwise, it can make the transient performance very bad. Okay? It can make, and when we maintain this difference in the angle small at the desired location, this means also that we are making their magnitude similar. So they cancel, their effect cancels out, and I get the performance of the system at the desired growth location. And we can verify this mathematically.
Professor, like this, we didn't only improve the transient, we improved the error also.
We improved the error. So now let us look at the system, combined system. Now our system design, so let me check where we are now, what step. So add an integrator. Okay, and we make here Ki over Kp to be equal 1 over 20 Ki over Ki. What is Ki over Kp? So we want this to be very small. So this is 1 over 20, right? We made it 1 over 20, correct? Okay. So now to make the 0 very close to the origin, which is the integrator, in order to minimize the alteration or the change in the transient performance. Now let us verify here the controller. So we are talking about step A. So the controller, now we have 1 plus Kp, right? S plus 0.5, 0.05. S plus 0.05, right, over S times 1 over S times S plus 1. What is the order of the system now, by the way? It's a third order, right? It is a third order. We increase the order of the system by 1. So this is S cubed plus S squared plus Kp S plus 0.05 Kp equals 0. Correct?
Yes.
Where plus 1? S cubed, this is S, because S cubed plus S squared Okay, plus KB times S plus KB times 0.05, right? And this can be written as S plus sigma, right, times S square plus 2 zeta omega ns plus omega n square equals 0. Okay, this is S plus sigma. We don't know where is sigma. What is S square? S square, we don't. What is our damping ratio that we want? 0.707, right? 0.707. So, and omega n, we want to maintain the, this is the whole thing, omega, this one, we want it to be 0.1. We want this to be 1, right? So we want this to be 1. If you are unclear about this, tell me why. Okay, this is 1s plus omega n square. Okay, and omega n square is what? Okay, so this is because this is the this one is the desired route location in order to meet transient performance. This is did not change, right? It did not change. So from which I can find when omega n is the same, because omega n on the root locus, we do not want to change omega n, and omega n it was we calculated it before, it was 0.7, right? Okay, so this is 0.7 square, this is 0.7 square is what? 0.5, right? This is 0.5. So this is S plus sigma times S square plus S plus 0.5. This is the desired system performance from which we can find sigma. So we compare this with our system here. So you will find that, okay, this is S cube plus S square plus 0.5 S plus sigma S square plus sigma S plus sigma times 0.5 equals 0. So you can compare these two and you will find that where is the sigma. So this is S cube plus 1 plus sigma S square plus 0.5 plus sigma S plus 0.5 sigma equal our system. What was our system? From the it is S square S cube plus S square plus KP S plus 0.05 kp. So we can find from this what is the value of kp. The value of kp. The system, we can achieve the system performance we want here by just adjusting a single parameter, which is kp. This is alternative A. All alternative A, we did achieve the performance with what? With a PI. With a PI. We added to our proportional controller integrator component. Integrator component. So we took the error, we integrated the error over time, and we controlled the system with the error and proportional to the integral of the error, the accumulation of the error over time, plus the error itself, plus a quantity proportional to the error itself. A quantity proportional to the accumulation of the error over time, plus a quantity proportional to the error directly. Yes. Well, let me, this is the example, you are doing it, okay, you are doing it in your study. So, you know, the exam is a requirement, right? The exam is a requirement. You need to, a good student, a perfect student does the following. He studies for his homework, he studies in a period in real time, and he tracks the curriculum very well. Now another student, he got busy with other things, so the error start to accumulate, right? So the divergence start to accumulate from the desired performance. So there is a big error now, and he takes this accumulation during the weekend and he sits down and try to correct, right? So the correction of the integral error, it takes basically the accumulation of the error over time. You don't see it instantaneously, you see it over time that, okay, I did not study yesterday, I did not make any correction day before yesterday, etc. I need to make now, I have a filing of things that I need to solve. This file of error makes you work, and yes, and it might make you unstable. It might throw you unstable. It might make you crazy and not perform. No, true. This is the behavior. Yeah, this is the behavior, and this is example. By the way, the first time I do it in my career, this example. Yeah. I hope it lasts in your mind. Okay. Yeah. Yeah. Yes. So. Solution B. We did discuss first solution. Solution B. We want to do another solution. Now it is not using integrator feedback, but we want to look at what kind of other controller that can solve this problem. Okay, so let us see what other kind of controller that can solve this problem. So I go back to the root locus. So this is my pole, okay, my system pole, and this is my second system pole, which is at -1. Right? This is the second system pole at -1. My desired poles, my desired performance should be here. This is -0.5, and if I cross it with this is zeta equal -0.707. So basically, again, I don't want to alter the root locus structure. Okay, so my controller, therefore, should be of the following form: 1 plus GC times G equals 0. This is my controller. This is what the controller problem that we deal with. Okay, and GC here, let me write GC as KP, okay, times S plus Z over S plus P. So I'm using a pole and a 0. Why I'm using a pole and 0?
Cancel another pole.
So I want the asymptotes not to change. I want only 2 asymptotes, right? Okay, so I want the asymptotes to be similar. Okay, so this is a pole and 0. Now, what is the gain deficiency I have? The gain at the desired root, it was 20 for achieving steady state performance. The gain to achieve the transient performance was 0.5. What is the ratio of the gain? 40. So I need to select Z over P to be 40. Z over P to be, okay, so I want to select, not Z over P, but the combination. The controller GC steady state, if I want the DC gain of the controller, DC gain, this is, we call it DC gain. What is the gain of the controller? This is KP times Z over P. And this should be equal 20. KP is the uncompensated system, which was 0.5 times Z over P. Therefore, Z over P should be what? Z over P should be 40. Z over P should be 40. i.e. Z should be 40P.
can change to the name.
Well, let us see. Uneasy, will uneasy work? Will uneasy work? Would uneasy work? Remember, at the desired root location, the difference between the phase of the pole and the zero should be small. Should be small. Right, should be small. And therefore, this means that I need to select P very small. P very small. Let P be 0.01. If you select P 0.01 times 40, it is 0.4, right?
Yeah.
Well, even for this case, this is too large. So we can select P to be 0.001. 0.001. So if I select P 0.001, so this is design, right? You tell me why you selected P, because I want to make this the angle contribution at the desired location minimum. And so if you come and tell me, okay, I want to select 0.0001, I'll tell you no problem. Go ahead. Now, where are the problems? When we go to the implementation. When we go to implement, theoretically on paper we can do it. Now when we go and implement it, when we start to select components, capacitors, resistors, etc., then we will face a problem. Okay, so
Because you won't have the values of the
well, yeah, so you need to select components that gives you this, and sometimes you end up with ending up with a very small motor and a huge gearbox. Okay, so you see, you want a torque very large. So you can take a very small motor and get a huge gearbox, and you get a very small RPM, right? But the torque is, you need the torque required. Okay, now in terms of cost and availability, etc., is this the best solution? No, you have to match impedance. Okay, and therefore here I go and I'll select, and you are right. Select whatever value you want, as long as the phase angle contribution at this desired location is minimal. So I can put the pole here and the zero next to it. Okay, so that when I draw the angle here from the pole and the zero, the difference is small. The difference is small. So this means that I need to move the pole of the controller very close to the origin. I want to drag. Ideally, I need to put it where? At the origin. So ideally, if I put it at the origin, then K, where is it? Z over P becomes what? Infinite. And therefore, that's why the PI controller works, it gives you zero error. Okay? Is this clear? So ideally, I want to drag this pole to the zero, to the origin. Okay? And then I can place the zero wherever I want close to that pole so that the angle is small between this angle here. This angle, I'm talking about this angle here. The angle of the pole or the angle of the zero minus the angle of the pole. So if I do this, I end up with the following. Now my controller GC equal KP times S plus, let's say here S plus 0.001 and this is S plus 0.04, right? So I have the okay, I have the desired desired controller, so I can check now and see a plot versus KP. So I have 1 plus KP times S plus 0.04 over S plus 0.001 times 1 over S times plus 1 times S. So I can check this. This is a third order system again. We increase the order of the system, right, from the second order to a third order. Okay. Now if this is 0, now the root locus problem now becomes the following. So I have the pole at the origin, and I have the pole of the controller which is very close to it, and I have the 0 which is here, and I have the second pole of the system which is at -1. So now look, if you want to get the asymptotes, how many asymptotes we have? How many asymptotes we have? Two. 3 poles -0, 2, right? The number of asymptotes 2. What is the location of the asymptote? -1 minus 0.001 plus 0.04 plus 0.04 over 2, right? So it is like that situation over there. So sigma, the asymptote, equal -1 minus 0.001 minus plus 0.04 over 2. So this is equal to 0.48 minus. Right? So this is, so I am making the asymptotes very close. So this is my, so I have, these are my asymptotes, minus 0.48. Now, what does the root locus look like? Now, this is different from the one before. We have two roots here, and then this will go and join here, and then they will split here, okay, and they will go to, and this is my desired location.
Sir, no.
This is k equal to k equal 0.5. This is k equal 0.5.
The one where the circle.
This one, yes, here, yes, yeah. I can show you in MATLAB that it would, this will work fine. Okay, and so this is the design for a controller to meet what? Steady state performance. We are addressing, remember, here we are addressing both, of course, but here primarily we are happy with the root locus, we are happy with the system dynamic. We don't want to make the system faster. Right? We don't want to make the system faster. The system is okay, but I want to fix the steady state performance. Because at the desired performance, the steady state would be too much error. So I want to make, basically, I want to use the same root locus, just increase the value of the gain corresponding to any point on the root locus. Make the gain much larger.
Sir,
Yeah.
where's the other asymptote?
When other asymptotes here, okay, look here, where are the asymptotes? How many asymptotes we have? 2. These are the asymptotes. How many asymptotes we have? This one and this one. We don't have any other. You want to invent new one? Fine. I don't have everything much. Okay, and what is the time now?
14
minutes.
Okay, any questions? Well, I went into the first session into going to the show them the controller to fix the transient performance. But I want discuss this. So these are the steps. What are the steps? Let us summarize. For designing a controller to fix the steady state performance. By the way, one more thing. This is why this called a lag controller. This called a lag controller. Why? Why?
There's a time lag.
When the zero, the lag and lead, it is the placement of the zero with respect to the pole.
Yeah.
If the pole comes first, then this is a lag controller. If the zero comes after, this is a lag controller. After the pole, right? So here we go from left to right to left. What comes first? Pole, and then the zero. This is a lag controller. This is a lag controller. And a lag controller, what is the phase angle there? There is a phase angle difference. Is the phase angle positive or negative? By the controller alone, by the controller alone, the phase angle is this angle here, this angle here, minus, okay, the angle of the zero minus the angle of the pole. Which angle is bigger? The pole. So the difference in the angle is negative. Any controller that its phase angle is negative is called a lag controller, meaning that the pole comes before the zero. The pole always comes before the zero. It will have a negative net phase anywhere in the S-plane, anywhere. But we make the minimum phase difference at the desired location. This is the idea. The key is to make the minimum phase difference at the desired location. Okay. Is this clear? So this is you are now ready to design a lag controller to fix steady state performance and transient performance. Okay. Now the problem is with the steady state. Why? Because we can achieve the transient, but the steady state becomes very bad. This is the idea. With the current system, with doing nothing, we can achieve the transient, but the steady state is bad. The other controller, which is to fix the transient, now the steady state we achieve it, but the transient is not good. Basically, you have, for example, a type 1 system, and you have steady state error specification on the position error. So you meet the position error, but your transient is bad. So you design okay. Any case, when we require, if our desired route now is somewhere here, if our desired route somewhere here to the left of the root locus, no matter what, we will not be able to make the root locus passing through this point the way it is. We have to shift, we have to make a controller to shift the root locus to the left. We have to shift the whole root locus to the left, and next time I will use the same example to explain it. Okay? So we'll see you next time.
So you said that this type of lag controller, right? So do we have lead controllers?
Yeah, we have
where the angle of the pole will be greater than the angle
exactly.
the angle of the zero will be greater than the
Yeah,
angle.
of course, yes. We have a lead controller. This a lead, a lag controller, a lead and lag controller, and we have a lead lag controller also.
Sir, will you be the office?